Okay, let's take a look at example 2. So we have a function that's very similar, a rational function right here. So x squared minus 2x plus 4 over x minus 2. So again, let's talk about the domain first, just so that we get that out of the way. And here we would say that it's all real numbers except 2. Right, and again, if we were to write that in interval notation, we have negative infinity to 2, together with 2 to infinity, but just not 2. Okay, so that'll help us as we go to find the critical numbers and the potential points of inflection that we'll know not to include 2 in there, even if it shows up as a critical number. Okay, first derivative, quotient rule, so f prime of x, bottom times the derivative of the top. Derivative of the top is 2x minus 2 minus the top, x squared minus 2x plus 4, times the derivative of the bottom, which is just 1, all over the bottom squared. All right, so then let's simplify the top there. I mean, I could factor out a 2 right here, but then I'm still going to have to multiply that out. So let me just multiply that out. So we end up with f prime of x is equal to 2x squared minus 2x minus 4x, so minus 6x plus 4, and then I'll distribute that negative through, so we get minus x squared plus 2x minus 4 all over x minus 2 quantity squared. 2x minus x squared is x squared. Negative 6x plus 2x is negative 4x, and 4 minus 4 cancels out, that's 0, and then we have x minus 2 quantity squared in the denominator. And I'm going to factor an x out here. Again, it's just going to make it a little easier when I go to figure out what the zeros of the function are. So we get x times x minus 4 over x minus 2 quantity squared. Okay. Next page, second derivative. Again, the first derivative, let me just write this here so that we don't forget, and the original function, so f of x is x squared minus 2x plus 4 over x minus 2, and then f prime of x, which we just found, is x times x minus 4 over x minus 2 quantity squared. Actually, I'm going to take the unfactored form for when we go to find the second derivative. That'll just make things a little bit easier. So we've got x squared minus 4x all over x minus 2 quantity squared. Again, when I go to find out what the intercepts are, I'll use that, but for finding the second derivative, I'm going to use this one. And so we have f double prime of x is the bottom times the derivative of the top, which is going to be 2x minus 4 minus the top, x squared minus 4x, times the derivative of the bottom. We're going to have to use chain rule for that. So 2 times x minus 2, decrease the power by 1, and then take the derivative of the interior, which is just 1, all over the bottom squared. So x minus 2 to the 4th. Both of them have an x minus 2 in it, and both of them have a 2. This one's obvious. This also has a 2 in it, so I'm going to take a 2 out of there. So we'll end up taking a 2 times x minus 2 out. It's going to be smushy. One of the x minus 2's will be left here. And then when I take out a 2 from this, I'll also have another x minus 2 in here. And then I've gotten rid of this, and so all that's left from the second term is x squared minus 4x all over x minus 2 quantity squared. All right, let's multiply this out. Again, sorry for the lack of space. First of all, this will cancel here. Whoops, I wrote squared. So this will end up, it should be to the 4th, so when I cancel that out, it'll be to the 3rd power. All right, so then this will end up being 2 times, When I multiply this out, I get x squared minus 4x plus 4. And when I distribute the negative through, I get minus x squared plus 4x. And it's all over x minus 2 cubed. When I simplify that, the x squareds cancel out, the 4x's cancel out, and I just end up with f double prime of x equals 4 over x minus 2 cubed. Okay, x-intercepts. Sorry, I'm wrong about that. I forgot that 2 right there. This should be 8 times x minus 2 cubed. All right, so we have f double prime, and then we have f prime. From now on out, I'm going to use this one. That'll help with the intercepts and other things, and then this was the original function f. Okay, x-intercepts, we need to set this equal to 0. And again, in a rational function, when we set f of x equal to 0, it's just really when is this 0? So we're looking for where is x squared minus 2x plus 4 equal to 0. Unfortunately, that does not factor. And if we use the quadratic formula, in fact, just to save space here, I'm going to use the discriminant. Again, that's the part underneath the radical. So it's the b squared minus 4ac to see if I even need to try and use quadratic formula. So b squared would give us 4 minus 4 times 1 times 4. That would be 4 minus 16, so this is imaginary. So no x-intercepts. All right, our only zeros are imaginary, so because we're graphing on a real x and a real y axis, we will not have any intercepts. All right, but for the y-intercept, we plug 0 into the original function. So we're going to get 0 minus 0 plus 4 over 0 minus 2. So we're going to end up with 4 over negative 2. So the y-intercept is 0, negative 2. All right, vertical asymptotes come from where is the denominator 0. So we just have a vertical asymptote at x equals 2. Horizontal asymptotes, this, again, the numerator is 1 degree higher than the denominator. We looked at situations like that where if this is, 2 or 3 degrees higher than this, it just goes to infinity. But if it's exactly 1 degree higher, it's going to go to infinity in a very controlled way. And so we're going to use, gosh, I'm going to do it down here. We're going to use synthetic division to see what that linear equation is for the slant asymptote. So no horizontal asymptote, but I'm going to put a slant asymptote in here. And again, we're going to talk about this on the next page, but I'm going to do it, well, let me just go to the next page just to give us some more room. All right. So here, again, we've talked about this already quite recently. Recall that a slant asymptote occurs when the degree of the numerator exceeds the degree of the denominator by exactly 1. To find it, use long division or synthetic division if the denominator is linear, which it is. To rewrite the rational function as the sum of a first-degree polynomial and another rational function. So what I'm going to do is I'm going to take our original, which is this. So I'm going to write in synthetic division the coefficients. So this is 1, negative 2, and positive 4. And then I'm going to take this. Again, x minus 2 means the 0 is 2. So instead of negative 2, I'm going to put in 2. It's always the opposite of that. And then do synthetic. That's a 1. 1 times 2 is 2. Negative 2 plus 2 is 0. 2 times 0 is 0. 4 plus 0 is 4. What that says is that the quotient, again, that numerator divided by the denominator, This is the remainder when I divide. This is the constant. And this is the coefficient of the x. And so what this translates into is x squared minus 2x plus 4 over x minus 2 is x plus 4 over x minus 2. Right, and so what that means is that we have a slant asymptote of x, y equals x. And here, we've seen this, again, a constant over, really what we saw in our notes was 4 over x to the n. But again, because this right here is so negligible as x goes to infinity, essentially we have this right here, even though that minus 2 isn't there. As x goes to infinity, this goes to 0. So even though we get a remainder, it's insignificant in the long run. In the long run, it's going to look like y equals x. All right? So let me go back and put that in here. So there is no horizontal asymptote, but there is a slant asymptote of y equals x. Let me clean that up so we've got some more room down here. Okay. Are there critical numbers? Again, let's go back to our first derivative, which is right up here. And we're looking for where is the first derivative equal to 0, or where is the first derivative undefined, as long as it was defined in the original function. So again, that's going to eliminate anything from the denominator here, because the denominator is 0 only when x equals 2, and we said already from here 2 is not in the domain. So really, for critical numbers, all we're looking at is when is the numerator 0. All right, so hopefully you can see that happens when x equals 0 or when x equals 4. All right, possible points of inflection, that is where the second derivative, which is right here, is 0 or undefined. All right, again, the 0 part is going to come from when the numerator is 0. But that will never happen. But we could also find places where the denominator is 0. Again, that only happens at x equals 2, and that's not in our domain. So possible points of inflection, none. All right, domain, we've already stated that. Negative infinity to 2, together with 2 to infinity. Again, that means the same thing as just x can't be equal to 2. All right, symmetry. We find f of negative x. Always when we're finding symmetry, put in negative x to see what happens. We want to know either does it equal the original function, does it equal the exact opposite of the function. If it doesn't, then we would say no symmetry. All right, so again, the original function was x squared minus 2x plus 4 over x minus 2, so I'm going to put negative x in. So we've got negative x minus 2. All right, I can already tell that's not going to work. This is going to change it to something that's not the same or exactly the opposite, but let's just multiply it out. We end up with x squared plus 2x plus 4 over negative x minus 2. Even if we say let's factor out a negative or something, it's not going to change anything. This is not exactly the opposite as the original, and it's not the same as the original. So there is no symmetry. Okay, so now we come to the point where we're trying to decide what our test intervals are. And again, to do that, we look at where are the vertical asymptotes. That only occurs at x equals 2. Where are the critical numbers? The critical numbers are at x equals 0 and x equals 4. And where are the possible points of inflection? And again, we said that there are no possible points of inflection. So again, I'm just going to put a little number line here and organize those numbers in order. So 0, 2, and 4. All right, so if you remember from the last example, the first thing we do is put down that interval that takes us up to 0. So this is going to be negative infinity to 0, and then we'll put in 0, the endpoint of that. And then we'll go from 0, next interval is 0 to 2. And then we'll say x equals 2. And then we'll go from 2 to 4. And then we'll say x equals 4. And then 4 to infinity. I've made all these tables so that they fit perfectly. So when you're doing these on your own, you're going to have to just count up how many. So how many points are there, how many individual points, and then you're going to always have one more interval because you're going to have the ones between and then one to the left and one to the right. Okay, and again, we can't find f of x on an interval. We can only find it at individual points. So let's cross out all these intervals. And then let's go through and say how these points ended up on our table. So x equals 0, this is a critical number. X equals 2, this was a vertical asymptote. And x equals 4, critical number. Okay, so then let's just go through and fill out our table. So at 0, again, we're going to be looking at this. At 0, we end up with 4 over negative 2, so we end up with negative 2 right here. When x equals 2, well, that ends up there because it's a vertical asymptote, so it's undefined. And when x is 4, this we actually have to do a little bit of work here. 4 squared is 4. This is going to be minus 8, so we have negative 4 plus 4 equals 0 over, let me just double check that again. 4 squared, I think I said 8. No, that's 16 minus 8, which is 8 plus 4 is 12 over 2, which gives us 6. Okay, again, this is going to test for increasing and decreasing, so we just need to know plus or minus right here, or if it's 0, we could say 0, or undefined, we could say undefined. In fact, we know all of these are going to be undefined because this is a vertical asymptote. Again, there will be some that we run across where it's undefined in later columns, but not in the original. Again, that will happen when we have fractional exponents that are between 0 and 1, where it would be defined in the original, but because it's not differentiable, it would start to be undefined. Okay, so let's do the sign here. So I'm going to pick negative 1 for here, and I'm going to go up to the derivative. And I'm going to use this form of it because it's already factored. So I put in negative 1, that's negative. This will be negative, so negative times negative is positive. And then down here, I'm going to get something negative, but I'm going to square it, so that's going to be positive. So I got positive up top, positive down the bottom, so this should be positive. All right, at x equals, sorry, I just put that in, I don't know if you saw that. At x equals 0, this is a critical number, so we should get that the derivative was 0, because that's how we got that number. So if I put in 0 here, yeah, 0 times negative 4, that's 0, so it doesn't matter what's going on in the bottom. We get 0 here. All right, I'm going to choose the point 1 in this next interval, 0 to 2. So when I put in 1 here, that's positive. That's negative, so top is negative. And then I put in 1 here, that's negative, but I square it, so that becomes positive. So negative over positive, that makes that negative. I'm going to pick 3 here. So I go up here and I pick 3. 3 is positive. 3 minus 4 is negative, so positive times negative is negative. Again, 3 minus 2 is positive, squared is positive. So I end up with a negative value right here. All right, I put in 4. Again, this should be 0 because it was a critical number. So if I put in 4 here, positive, 4 minus 4 is 0. Yep, that's 0. And here I'm going to test the point 5. So when I put that in the first derivative, 5, positive, 5 minus 4, positive. So positive times positive is positive. 5 minus 2 is 3, squared is positive. So this is positive. All right, now we repeat the same thing again for this column, except this time we're plugging those test values into f prime of x, which is 8 over x minus 2 cubed. Again, 8 is always positive right here. So really, it's this guy that gets to decide. X minus 2 might be positive, it might be negative, but whatever the sign, cubing it is not going to change the sign, right? So always positive, and then this is just going to depend on whether this is positive or negative. All right, so again, I chose -1 for my first interval. So 8, positive, -1 minus 2 is negative. Again, cubing it keeps that negative. So positive over negative, this is negative. All right, I put in 0 for x for the second value. 0 minus 2 is negative. Cubed is negative, so positive over negative, negative. The next interval is, our test value is 1. So 8 over 1 minus 2, 1 minus 2 is negative, so this is going to be negative. Our next value is x equals 3. So 3 minus 2, positive, cube it as positive, put it under a positive number, positive. That should happen for all of these because again, I'm now picking values that are greater than 2. So when I subtract 2 from it, I will get a positive number. So again, this is going to be positive, and that's going to be positive. All right, so let's fill in our characteristics. So again, this is increasing and decreasing. This is concave up or concave down. So here I've got it's increasing and it's concave down. Here, again, I'm using this little cheat here to help me remember why this is happening, and it's because this is going to be a critical number. So it might be a relative max, it might be a relative min. And so we could use the first derivative test here, which says that if it goes from increasing to decreasing around a critical number, that is a maximum. Again, it goes increasing to decreasing, I must have a max. So this is a relative max here. All right, this is decreasing and concave down. This is decreasing and concave up. All right, here again, we're checking. This is a critical number, which means it could be a max or a min. So we're going from decreasing to increasing, decreasing to increasing. That means this is a relative min. And then finally, this is increasing and concave up. Okay, let's graph it. So let's see, we need to graph, boy, we have a lot of information here. We have no x-intercepts. We have a y-intercept at 0, -2, so that is right down here. No horizontal asymptote, but a slant asymptote at y equals x. That means all along here. We're going to end up just drawing a dotted line along there. I just might have misplaced that dot. All right, so it's going to look something like this. Vertical asymptote at 2. Right, at 0, -2, which happens to be the y-intercept, there is a critical number there. At 4, 0, there's going to be a relative, no, sorry, my bad, 4, 6, I was looking at that column, 4, 6. There is going to be a relative min, 1, 2, 3, 4, 5, 6, right here. And then, let's see, what else do we have? I guess that's it. Vertical asymptote, slant asymptote, 0, -2, 4, 6, we've got that. Yeah, I guess that's it. Okay, so let's go from here. From -infinity to 0, it is increasing and concave up. And there are no points over here that we can choose from. But I know if it's increasing and concave up, again, this slant asymptote, the function has to approach that. So it's going to get pretty close. And then it's also got to get pretty close to this one. And so we'll just say it's going to look something like this. Again, we're not going for exact in here. We just want to get a general idea. Oh, I'm totally wrong about that. So wrong. I'm just looking at this little point right here and I'm like, what's he doing down there? Okay, increasing concave up. That means it's this way. Something like this. Oh my gosh, I'm so misspeaking. Increasing concave down. That's what's going on here. My gosh, it's getting too late for me to be making this video. All right, this is a relative max then. All right, then it's decreasing and concave down. That's where it's going to do a turn like this and start hugging this vertical asymptote. Sorry, I don't know what I'm saying. Increasing, concave down. Again, so it's downward like this, and then it's going to switch to being decreasing concave down. Also, let me mention here while I'm thinking about it, we could use the second derivative test here to say at a critical number, if I check the second derivative, if it's down, concave down, then that means it must be a max. Because again, if it's concave down, that can only happen if that value is a maximum, which it is. Okay, and now over here on the other side, from 2 to 4, all right, so again, 2 is our vertical asymptote, to 4, where our critical number is, our other critical number, it's decreasing but concave up. So something like that. And then, again, we could also confirm this relative min aspect by using the second derivative test. It's concave up there, which means it has to be a min. Right, but then from 4 to infinity, it's increasing and concave up, which means when we come back in here, we've got to do something like this. So it's increasing and it's still concave up. All right. So again, next page, we've already filled that part in because we needed to find that slant asymptote for the function that we just did. Okay, let's look at example 3.